Okay, where were we? I believe we were about to go over the states or phases of matter, or in other words, solid, liquid, and gas. And we can look at the diagram in the book or the PowerPoint that shows examples of solids, liquids, and gases. And you can see the main difference is how close the particles are to each other. In a solid, they're very close to each other. In a liquid, they're a little further apart and have more freedom of movement because of that. The particles in a solid are so close together that they really can't move relative to one another except for vibrations. They can't move translationally, is what it's called, from place to place. In liquids, the particles are a little further apart, and so they do have not only vibrational freedom, where they can vibrate in place, but they can move around and past one another too, with a little bit of resistance or restrictions on their movement. Gases, in gases, the particles are far apart, and so they have total freedom of movement. They can vibrate in place, but they can move from one place to another very freely. And in fact, the particles in a gas are in constant, very high speed motion at any temperature around room temperature. And now we need to look at the scientific reasons for why that is. Why are solids, liquids, and gases the way they are? And it's the scientific reasons that are the things that you might not immediately think of, even though we're all familiar with solids, liquids, and gases. For solids, the number one reason the solids are the way they are is that they have strong intermolecular attractions. Okay? And yes, that's named after me. Intermolecular attraction, that was a joke, by the way. Intermolecular attractions are, well, if you think about it, it's just what it says, attractions between molecules. And the substances that we know of as solids just happen to be made up of molecules that have very strong attractions for each other. And so when they get near each other, they clamp onto each other and they hold on for dear life. And that's why solids are solids. It's the strength of the attractions between the particles. So the particles are more or less fixed in place. I mean, you can smash the solid, most solids anyway. You could smash, and that would get them apart from each other. But most of them would still be fixed together in the chunks. So the particles are more or less fixed in place. But nonetheless, the molecules can vibrate in place. The vibration of the molecules is something that happens a lot more than we realize. Even the most solid you can think of, a piece of granite or a piece of lead, the individual atoms or molecules in those solids are vibrating in place, and they're vibrating pretty quickly, actually. And it's just that it's happening on such a small scale that we don't notice it, but it is happening. And the vibration, the amount or the vigorousness of the vibration is related to temperature. Basically, the hotter it is, the more the particles vibrate. The cooler it is, the less they vibrate. But they never actually stop vibrating, no matter how cold it gets. They'll always be vibrating a little bit. And the little squiggle just means more or less, no translational movement. That is movement from place to place around each other. They can't do that in solids. The volume and shape of solids would be fixed. That is, they don't change easily. And because the particles are already right up against one another, they're about as close as they can possibly be, solids are not compressible. You can take a solid and try to squeeze it to make it smaller, and you can't do it. Even if you take a solid like foam rubber or something like that, and squeeze it, you might think that you're compressing it, but foam rubber or styrofoam or things like that, they're made up of solids that have a lot of air spaces between the solid particles in them. All you're really doing is you're compressing the air spaces, not the solid. So solids themselves, not compressible. There are a couple different types of solids. Excuse my arm. Because the particles are fixed in place, we can talk about the arrangements of the particles. There are some solids that are known as crystalline solids. And a crystalline solid is just one that has a regular order. That is, the particles that make the solid up are arranged in a regular repeating three-dimensional pattern that repeats over and over again throughout the structure of the solid. So it's a regular arrangement. Some examples, first I'll mention some examples, would be ice crystals. Ice is definitely crystalline. Diamond is crystalline. Sea salt is crystalline. And some plastics are crystalline. And one thing about crystalline solids is that because of this regular repeating pattern of atoms or molecules, kind of like in the structure of diamond that we see here in the book, you're able to get very flat, even surfaces if you cut the structure in the right place. So if you cut it in the right place, you can get it to sort of break between the layers of atoms, and that gives you a very flat surface like in a diamond. Actually, even in a salt, in table salt, if you look at the grains on a very fine level with magnifying glass, you'll notice that the grains tend to be little cubes, or maybe not perfect cubes because they weren't broken deliberately, they were just ground up in a machine. But they are more or less cubes, and they have a lot of flat surfaces and a lot of sharp edges and 90-degree corners. And that is because salt's crystal pattern leads to the substance breaking along those planes of molecules, or in this case, between the planes of sodium and chloride ions, and that leaves a flat, smooth surface. On the other hand, you have not crystalline, better known as amorphous. Amorphous comes from the Greek phrase that literally means without form or without shape. And what this entails is an essentially random arrangement of the particles. Okay, and this goes on in three dimensions over and over again. And like I said, it's more or less random. The particles are just sort of thrown together. There's no regular pattern or arrangement of the particles. And probably the best known example of an amorphous solid is glass. Glass is amorphous. It's made up mostly of silicon dioxide molecules, but other stuff too sometimes. And those particles are arranged more or less randomly throughout the glass. And that's one reason that glass is so unpredictable in its behavior. When you were a kid, you may have experienced broken windows or not experienced them, just depending on various random circumstances. Sometimes you can throw a ball and it'll hit a window really hard and nothing happens. Other times you just barely touch it and it shatters. And that's just part of being amorphous. The behavior is kind of unpredictable. Glass is really hard to cut too. If you want to cut it, like, put in a new window after you break the old one with your ball, cutting the glass along a nice straight edge in order to get it to fit in the frame, that is really difficult. That takes a lot of skill. And it's because the particles just go any which way. It's not like a diamond where you can actually look at it carefully and decide where to cut it and have it come out in a nice straight line. With an amorphous solid, it's pretty much random. And you really just have to count largely on luck as well as skill. Also, some plastics. Some plastics are crystalline, some plastics are amorphous. And sometimes you can actually see the transition between amorphous and crystalline yourself. If you take transparent polystyrene, which is the rigid plastic that's used in a lot of cookie trays and things like that, that's, it's kind of semi-rigid. Look for the triangle, the recycling triangle on the plastic, and if it says PS inside it, that's polystyrene. And so if it's transparent, just take a piece of it and start bending it back and forth in your hands. And you'll notice as you do that, it turns white. And that's because it starts out amorphous, which is transparent. But as you bend it back and forth, you're forcing the molecules into alignment with each other, and it becomes more and more crystalline over time. And crystalline polystyrene is white. So you can actually see it happening. All right, well, that's solids for now. Next, we get to liquids. Okay, liquids are like solids, only less. Liquids have moderately strong intermolecular attractions between the particles, which means the particles are attracted to each other, but not as strongly as in solids. And that explains the properties of liquids. The particles are close to each other. But not quite as close as they usually are in solids. Okay, they have vibrational and limited translational movement. Remember, translational just means that you can move from one place to another around other particles. Okay, so it's limited because there is a certain amount of resistance to movement. Both of those are related to temperature. So the higher the temperature, the faster the particles vibrate in place, and also the more they tend to churn around and move around and past one another. Because the particles are not quite as close together as they are in solids, liquids can be a little bit compressible, but not significantly. Okay, so they're not very compressible. For all practical purposes, I would say that liquids are not compressible. And they have a fixed volume but no fixed shape. And that is part of the ability of the particles to move around and past one another, is that when you put them in a container, they will stay about the same distance apart from each other. They don't move apart and they don't get any closer, but they can flow around and past one another, and so they take the shape of the container. And some examples of liquids, of course, water, probably the first one everybody would think of. Alcohols, gasoline. The element mercury is also a liquid. And they all have these properties, more or less. Gases, on the other hand, have no intermolecular attractions. No intermolecular attractions at all. And that means that the particles in a gas tend to be far apart from each other. And they have total freedom of movement because there's nothing holding them back. They're not attracted to each other. And so that's vibrational and translational freedom of movement. And both of these are related to temperature. And in fact, in gases, temperature is a major factor in how fast the particles are moving. With liquids and solids, there's a small effect, but it's really big in gases because there's nothing else holding them back. Because the fact is, in gases, the particles are in constant motion. Not only are they moving very quickly, even at moderate temperatures like room temperature, the particles of nitrogen and oxygen in the air are moving, I think, something like about 500 miles an hour, just at room temperature. And we don't notice them hitting us because they're so small. But the particles in a gas will be in rapid, straight line motion constantly. In random directions, unless there's a draft or a breeze or something like that. And because of this, the gas particles will basically keep moving in a straight line indefinitely until they hit something, like the wall of the container or another gas particle, and then they will bounce off and move in another direction until they hit something else. Okay? There's no fixed shape or volume in a gas, and gases will take the shape of their container and expand to fill it. Okay, and taking the shape of the container and expanding to fill it is part of the fact that the particles in the gas are in constant, rapid, straight line motion. So if you put gas particles into a container, even if it's a really big one, they're going to basically zigzag around and find the outer limits of that container pretty quickly. And that's what we mean by filling it. There will be gas particles everywhere within that container almost immediately. Gases will mix with each other immediately, very quickly. And homogeneously. We haven't really defined homogeneous yet. It just means an even distribution. So if you put two gases together, like the nitrogen and the oxygen in the air, they will mix together homogeneously. So the concentration of one of them's oxygen, say, will be the same everywhere in the atmosphere. And it doesn't matter what the two gases are. This is, this is different from liquids, for instance, because whether liquids will mix homogeneously or not really depends on what the liquids are, if the molecules are attracted to each other or not. With the gases, the molecules are definitely not attracted to each other, but none of them are attracted to each other. And so they can mix evenly. And they're easily compressed because the particles are so far apart. When you compress a gas, you're really just compressing the empty space between the particles. You're not really compressing the particles themselves. If you take something like a Coke bottle or a Pepsi bottle that's empty, one of the plastic bottles, and put the cap on it tightly and then squeeze it, you notice how easy it is to squeeze it. And that's because you're just compressing the space between the particles of air within the bottle. And so that's really easy to do. Examples of gases would be things like oxygen, helium, carbon dioxide. Those are all gases. If you want to classify matter by its composition, then there are ways to do that too. One of them is by substance. And as I said, when you talk about substances, the assumption is that you're talking about a pure substance. So that's why I put pure in parentheses there. And a pure substance would be one that's made up of only one type of atom or molecule. And that means that the composition would be the same everywhere within any given sample of this substance, because it's the same stuff everywhere. And that's true not only within a sample, but also from one sample to another. Because if it's a pure substance, it only consists of that one type of atom or molecule. And so the composition should not just be the same everywhere within that one sample. It should be the same in other samples of that substance too. If you have a glass of pure water, then the composition of pure water is H2O. And it should be H2O everywhere within that glass of water. And it should be nothing but H2O everywhere within any other glass of pure water from anywhere else, because it's the same substance. Okay, on the other hand, you can have mixtures. And these are made up of more than one type of atom or molecule. Okay. And because you've got more than one thing in a mixture, that means the composition can vary, not only within a sample, but also from one sample to another. I'm putting the within a sample, whoops, in parentheses, because there are some mixtures where that's possible and some where it's not. But this is always true for mixtures. The composition can always vary from one sample to another. If you think of salt water, it is certainly possible to have salt water that's saltier than another sample of salt water. Some oceans, like the Dead Sea, are saltier than others, like the Atlantic Ocean. So, so it is possible for the amount of salt in the water to vary from one sample to another. Now, looking at substances and mixtures in a little more detail, pure substances can be either elements or compounds. Okay, the elements are sort of the simplest building blocks of matter. And they cannot be chemically broken down into anything simpler. And there are about 120 known. Most of them are naturally occurring, but a few of them are artificial, made in the lab. And these are the substances that are listed in the periodic table. So, if it's an element, it's in the periodic table. If it's in the periodic table, it's an element. And we'll get to those in more detail later. A compound would be made up of two or more different elements. And it's important that they be different elements. Otherwise, it's possible to have a molecule that is an element, for instance, as opposed to a compound. In order for it to be a compound, it has to be two or more different elements. And those elements have to be chemically bonded together in a fixed and definite ratio. Like, for instance, H2O. Water. Each molecule of water contains two hydrogens and one oxygen. That's your definite ratio, two hydrogens for every one oxygen. There are many millions known. Many of them are naturally occurring, but many are also artificial, and they're made up of the elements from the periodic table. Now, looking more closely at mixtures, the two types of mixtures that we're concerned with right now would be homogeneous and heterogeneous. But again, I see that we've reached the approximately 30-minute mark. So I'm going to leave you in suspense until the next part of the lecture when we'll pick up where we left off here. See you in a moment.